So I would like to present today some results of a very recent paper that we have published in the ALX collaboration, which I'm going to introduce later. And this is about the discovery of a galaxy group at redshift 4.3 behind the massive galaxy cluster El Gordo. So the basic question behind this work is, are submillimeter galaxies and millimeter galaxies alone? So we have some pieces of evidence from works over the past 20 years that some millimeter galaxies could trace active sites of star formation, not by themselves, but also their environment could be rich in star-forming galaxies. So some examples that we have here from the recent years include the discovery of protoclusters or galaxy groups, normally dominated by very bright submillimeter galaxies at different redshift, from redshift 2 to even redshift of 6. But the majority of them are characterized by this fact that the submillimeter galaxies are really bright. So in the sub-Milichanski regime, we see some galaxies, but not so many. There is one or two cases only precedents about sub-Milichanski galaxies found in galaxy groups, and this has been discovered through lensing analysis. This is from an old piece of work from Jean-Paul Neve and collaborators, who discovered a submillimeter galaxy linked to a galaxy group behind a massive galaxy cluster. And this was a case of a group at redshift 2.5. The case I'm going to present today, it corresponds to a much more compact group and to a higher redshift, redshift 4. So the ALMA galaxy sitting in this group I will talk today has been observed with the ALMA Lensing Cluster Survey, which is an ALMA large program to map 33 lensing clusters with band 6 for a total of 88 square arc minutes, and to a very nice depth of 80 microchanskis per beam on average. The PI of this survey is Kotaro Kono in Japan, and the collaboration is composed of almost 100 scientists. So the plot you see here compares the depth and area of several large programs which have done 1 millimeter mapping in ALMA, band 6 mapping. And as you can see, of course, ideally you would like to be in the right-hand lower corner of this diagram, because there you have maximum area and maximum depth. And as you can see, ALX is located here, which means that it has one of the most optimal combinations of area and depth that we have so far for 1 millimeter mapping. So among the 33 clusters mapped in ALX, there is one which is El Gordo, which is a very famous massive galaxy cluster. And it's very famous because it's really very massive. We are talking about a total mass of 10 to the 15 solar masses. And this galaxy cluster is at redshift 0.87. And this cluster has been observed several times with the Hubble Space Telescope, with ALMA, and with the VLT. And the observations I will talk about today involve ALMA data and also VLT data from the Muse spectrograph. For those of you who are not so familiar with Muse, Muse is an integral field spectrograph which has the very special characteristic of providing field spectroscopy over 1 square arc minute in a single shot. And this makes it a unique instrument in the world, and it's very sought after, because having this power of giving spectroscopy over such a large area in a single shot allows for many serendipitous discoveries. And the wavelength range in which it operates is mainly the optical bands, between 4,700 angstroms and 9,300 angstroms. And basically, at high redshift, we use it for the study of Lyman alpha emitters between redshift 2.9 and 6.7. So using Muse and observing El Gordo, we found that there is a nice galaxy group at redshift 4.3, which is magnified to a point, and there are 3 different images produced by the lensing cluster. This is what you can see here. The source indicated with green squares are those which belong to the Muse galaxy group, and you have the group replicated in 3 images. The magenta curves that you see in each case represent the areas where you can see the ALMA source at 1.2 millimeters. Very interestingly, this ALMA source actually was known before, because there were previous millimeter analysis of El Gordo, but people thought that these were 3 different galaxies. They never realized it was the same galaxy amplified 3 times by the cluster. So basically, it's a very compact group. As you can see, this is 10 arcseconds, so the area is very, very small, and we are going to see it better when we zoom in into the ALMA source. So this is a postage stamp of the ALMA source next to one of the Muse galaxies. The ALMA source is here, and as you can see, the ALMA source can be in IRAC, in Spitzer IRAC in channel 1 and 2, but not in the HST images. So the IRAC the ALMA source cannot be detected in Muse, cannot be detected in HST, only in ALMA and in Spitzer. So normally it would be very difficult to have a redshift for this source. It's very difficult to obtain a redshift, but thanks to the lensing model of this cluster, we could obtain a probability density distribution for the redshift, which is very well centered at the redshift, at the same redshift of the Muse sources, confirming that this ALMA source is in part, is also part of the same galaxy group. So these are the spectra that we see in Muse. As you can see, this is more of a crosstalk between optical and submillimeter. Here is just how the different Muse sources look like. They are Lyman alpha emitters, 2 of them, they are confirmed. And the source which is associated with the ALMA source actually has Lyman alpha in absorption, very clearly Lyman alpha in absorption, and it seems to be quite an evolved galaxy with respect to the other 3. So we did have SED properties based on the HST bands, and we did that for the Muse sources. That was pretty simple because these galaxies are bright in the optical, but we also tried to do that for the ALMA source. And this was tricky because these galaxies, of course, only have upper limits in HST. But we used the Spitzer photometry and the known redshift, the redshift known because of the lensing models, to try to set and derive parameters for the ALMA source, particularly the stellar mass and the star formation rate. Of course, the star formation rate was based on the submillimeter fluxes, not on this, but the stellar mass is based on this SED analysis. For the other galaxies, with this SED analysis, we can obtain also the stellar mass and also the star formation rate. But the star formation rate in this case comes from the UV flux, the rest frame UV flux. So with these properties in hand, what we did was to locate all these galaxies in the famous star formation rate versus stellar mass plane. And here you can see 2 panels, okay? And basically the galaxies that you see from this work are the same in the 2 panels. But in the panel on the left-hand side, we are comparing to lensing sources, while in the panel of the right-hand side, we are comparing with field galaxies. And basically you see that the ALMA galaxy clearly sits on what we call the star formation main sequence. And this does not come as a surprise because other works have concluded that mainly submillimeter galaxies, most of them are main sequence galaxies and not starburst galaxies, not galaxies with particularly enhanced star formation activity. Now, for the other galaxies, the galaxies which are in the Muse group, you have a mixture. Some of them sit on the main sequence, but some of them are clearly on the starburst envelope that I can discuss later after the talk how this envelope has been considered. On the right-hand side, you have a comparison with field galaxies, galaxies mainly that come from the cosmos field, and the green points particularly are submillimeter galaxies from the Alpine program. And as you can see, also in consistency, most of the submillimeter galaxies sit on the main sequence, except a few, which would be in the starburst cloud. Now, note that the regime in stellar mass probed by the submillimeter galaxies is quite different to the regime probed by the small lens galaxies that we have here. So the incidence of starbursts appear to be much higher at small masses than what you see at high masses. And this one could be one of the main reasons of why the classification for these galaxies is different. But this is interesting because as far as we know, starburst galaxies make at most 10 to 15% of all the star-forming galaxies at any redshift. Even at high redshift, starburst galaxies are no more than 15% of all star-forming galaxies. But here, within the compact group, we see that half of the sources of the Muse sources are starburst galaxies. So this is quite a different story. So the explanation for this is under discussion. So what are the takeaway points, I mean, from this analysis of this high redshift galaxy group? What is the difference with respect to other analysis? Well, I think this emphasizes very important points, like, first of all, doing a multi-wavelength analysis of the same galaxy group and combining the ALMA data with optical data yields a much clearer picture of the nature of the ALMA galaxy and also in its environment. Again, this galaxy was known before, but it was supposed to be completely alone, and they were supposed to be 3 different galaxies, not one surrounded by a galaxy group. The second point is that lensing can help very much to determine the properties of the ALMA sources, which are HST dark. Of course, when we have JWST, we will not need this anymore because we will be able to do a spectroscopy of these sources on a common basis. But so far, either you get ALMA redshift, which is quite costly and quite difficult, or you can use lensing as an alternative way. And the final point is that starburst galaxies might be more common than what we think if we look at the right environment. Although here we are still not sure if the reason of this high incidence of starbursts is due to the group, which is very compact, or also to the fact that we are looking at to galaxies of very low stellar masses.